In this video, we're going to define linear bounded automata and give a few results about what they can compute and the computation class that they define. Let's start by defining linear bounded automata, LBAs, if you will. They're very much like Turing machines, only they're slightly restricted. So it's essentially a Turing machine with one small constraint on the tape. And that constraint is that the tape is limited to the size of the input. Okay? The tape head is not allowed to move off the end of the tape. With a Turing machine, the tape is unlimited in one direction. Okay? It's an infinite tape filled with blanks off to the right. But with a linear bounded automaton, the tape ends at the end of the input, and you can never move off the end of that. If you try to move to the right, it just sticks there. Exactly the way a Turing machine, a normal Turing machine, sticks if you try to move to the left, off the left end of the tape. So here are two different machines applied to two different inputs. Okay, this input has 7 symbols, and so the tape is limited to 7. And here the input is a much longer input, approximately a dozen characters or so, and so the tape is limited to that many cells. It turns out that linear bounded automata are not as powerful as full Turing machines, but they are really quite powerful. It doesn't seem like they should be so powerful because it seems like we've limited their tape to a very small amount, but in fact they're really more powerful than they might first appear. In all other respects, the linear bounded automaton is just like a Turing machine, and in particular we can always have additional symbols in our tape alphabet beyond the input symbols, the symbols that are used to express the input. So our tape alphabet can actually be larger than the input alphabet. Remember that we used gamma to characterize the tape alphabet, and we used sigma to characterize the input alphabet, and we assumed that every character in sigma was also in gamma. Gamma contains as well the blank symbol and some other symbols that we might want to use during the computation. So we can have a larger tape alphabet, and we can use that larger tape alphabet to store more information on our tape, even though our tape is limited in length. Okay, if, for example, our input alphabet consists of just zeros and ones, we could, for example, have a tape alphabet that also had 2 additional characters, and with 4 possible combinations, we can essentially store in each tape cell not only the 1 bit that corresponds to the input symbol, but an additional bit of information to affect our computation, to make use of in our computation. So by increasing the tape alphabet, we can increase the amount of information we can store in each cell of the tape. Equivalently, we can say, instead of increasing the tape alphabet to enlarge the amount of memory, the amount of information we can store, we can restrict our machine to using only a small portion of the tape, rather than allowing an infinite tape to be available for any computation. So that's where the name linear bounded automaton comes from. So the idea is that we get no more or less power if we redefine linear bounded automaton to say that it's a Turing machine where the size of the tape is limited to some linear function of the input size. Now here's an example. We're saying that in this particular linear bounded automaton, our tape is limited to 3 times the size of the input. So, for example, if our input is only 2 symbols, we get 6 symbols, 6 cells of tape to make use of. That would be a short problem, so we have a short, we can call this a working memory of 4 extra cells. But the size of the working memory is linear in the size of the input. Over here, we have an input that's twice as large, and we have twice as many cells to work with. We have 12 cells to work with. So the tape size is limited to 3 times the input size. So changing the definition of linear bounded automaton in this way to just restrict our tape to being a linear function of the size of the input doesn't add any more power to the linear bounded automaton, and so these two definitions are effectively equivalent. Remember our old friend, the acceptance problem for Turing machines? Well, here's the equivalent problem for linear bounded automata, A sub LBA. As in the case of the acceptance problem for Turing machines, we're given a machine, or more precisely, we're given the description of a machine, as well as a string to run that machine on. And we say that this pair is a member of the language if M is a valid machine, in this case a linear bounded automaton, and M accepts W. And it turns out that, surprisingly, this problem is decidable. Although the acceptance problem for Turing machines is undecidable, the acceptance problem for linear bounded automata is decidable. How can we prove this? Well, let's consider some potential string, and we're trying to determine whether it's a member of the language. In other words, we're trying to solve some particular acceptance problem for linear bounded automata. Well, we're given a linear bounded automaton, and we're given a particular input to that. So from those two elements, we can determine the number of states in the linear bounded automaton. The size of the tape alphabet is part of the specification of the linear bounded automaton. And the length of the tape can be computed from the size of the input. So we know each of these. Q, we can use little q to indicate the number of states. We can use G to be the size of the tape alphabet. And N is the length of the tape. So now we can ask, how many distinct configurations can we make with these numbers? And the answer is this right here. Q times N times G to the nth. In other words, we have Q different states, and we have N possible places that the head can be positioned. N is the length of the tape. And the contents of the tape, well, we've got N characters in the N cells in the tape, and each cell can contain one of G possible alphabet symbols. So G to the N possible tapes is the number of tapes we can have. So combining all these things, multiplying them together, we get Q times N times G to the nth power. Now, this may be a big number, but it's finite. In fact, it may be a really, really big number, but it's still finite. For example, if our tape alphabet has a modest 26 symbols, such as the English alphabet, and the tape is limited to, say, 1,000 cells, then what does this number look like? Well, 26 to the 1,000th power. To say that this is a big number is really a tremendous understatement. It's not a big number. It's a really, 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 really big number, a number beyond any kind of conception or any kind of realization in any real-world setting. I mean, this number doesn't really describe anything that could ever exist. It's such a large number. But nonetheless, it's still a finite number, and we can imagine that number to some extent. And we know that it is actually a number, and it is finite. So the point is that there is a finite number of distinct possible configurations. It's not an infinite number of configurations. With a Turing machine, of course, the tape can grow and grow and grow, so we cannot put this kind of bound on the possible contents of the tape. Here, our tape is limited to some linear function of the length of the input, so we can bound the size of the tape and therefore bound the number of distinct possible configurations that the machine can be in over the course of any computation. So I said before that the acceptance problem for linear bounded automata is decidable. And now we're going to sketch out the proof of that. This language is the set of strings such that the strings are pairs, and the first part is a description of a linear bounded automaton, and the second is an input to that, and that linear bounded automaton, if run on that string, would accept it. And the idea is we can decide whether some string is a member of this language by just running M on W. M is a description of a machine. We can simulate M on W. We couldn't do that with the acceptance problem for Turing machines because it might not terminate. So we have to address that problem here. The machine could accept or reject, but it could also loop. And so how can we say this is decidable? How can we detect that M is looping on W? Well, consider this. If the machine ever enters a configuration that it's already been in, then it'll loop forever. Okay? The configuration describes the entire state of the machine. And if it enters a configuration that it's already been in before in any particular computation, then it will do exactly the same thing as it did before, and it will loop. So if it enters a configuration that it's already been in, then it will do exactly what it did the last time it was in that configuration and keep re-entering that configuration and loop forever. Now we just showed that there are only finitely many possible configurations. So what we can say is that if the simulation goes on long enough, in fact if it goes on this long for this many steps, then it must re-enter one configuration that it's already been in. Okay, there are only so many configurations, and after this many steps, it will have gone through possibly all of those configurations, and at that point must have to re-enter a configuration that it's already been in. And therefore, if the simulation goes on this long, it must be looping. So at that point, we can just stop the simulation and only run the simulation for q times n times g to the nth steps. And if it hasn't halted by then we know it's looping, and so we know that m will never accept w, so we can reject. And in that way we can see that this problem is decidable. The language A sub LBA is decidable. Well, before we leave the subject of linear bounded automata, I just want to mention again that they are very powerful, almost as powerful as Turing machines. They don't have the full power of Turing machines, but they have a lot of power and they're close. And I'm just going to present these problems. These are decidable not only by a Turing machine, but they're also decidable by a linear bounded automaton. I'm not going to present any proofs for these, but I'm just going to state, as a matter of fact, that these problems are decidable by a linear bounded automaton. So these are not requiring the full power of Turing machines to decide. The acceptance problem for deterministic finite state automata, the acceptance problem for context-free grammars. And this is the parsing problem right here. Given a grammar and a string, does that grammar accept the string? Well, you don't need a full Turing machine to do that computation. It's a linear bounded automaton will suffice. Given a deterministic finite state automaton, does it accept anything? Is the language empty or not? That's decidable by a linear bounded automaton. Same thing for context-free grammars. Given a context-free grammar, will it accept any string at all? So these are some sample problems that we saw could be decided by Turing machines, but in addition, they can be decided by a linear bounded automaton.